Howdy, everyone. Professor Parks, and this is yet another of my series on the solar system. If I sound a little weird, it's because I'm finally getting around to playing with my lavalier mic. I just did a video. I just posted a video where I use it, and I show a video of Venus that we took yesterday. I'm not exactly sure if I like it or not, but we're going to go with it today. So if you haven't checked out that video yet, which you probably haven't because I just uploaded it, yes, uh, you would in fact be correct. Uh, if you haven't checked out the video on Venus, I highly recommend it. It is very cool in that it shows pretty much what you can see through our telescope in terms of that planet, and it shows the fact that Venus goes through phases very, very well, because the moon was, or the Venus was in quarter phase. It still is, because it was taken, this video was taken yesterday, but anyway. So let me load up my slides and say howdy to Nimrod, Nerd Alert, and Charlie Welsh. Apologize for starting a bit late. Kind of got wrapped up in so a little bit of work stuff, a little bit of flat Earth stuff. So I may be taking a break from that, to be honest with you. I don't know. It's starting to make me, dealing with flat Earth content is starting to make me feel like a person that I don't want to feel like being. So it's making me more angry. So yeah, who knows? All right. So what are we talking about today? Howdy, Tiny Captain. What we're talking about today is, and again, I apologize if the mic is weird, because again, I'm trying out my lavalier mic, and hopefully it goes well. In the last video I made, it was kind of scratchy. All right, so we're talking about what, when I was growing up, when I was coming up, when Pluto was still technically considered a planet, these worlds were known as the Jovian worlds. But since then, we have gotten more information about the universe, particularly in terms of planets going around other stars. And at one point, and I can't really identify when, but at one point, the Jovian worlds got subcategorized. In that Jupiter and Saturn are now considered the gas giants, and Uranus and Neptune are now considered the ice giants. Why exactly? I don't know. I don't know whether or not that subcategory is needed, but there is some justification for it, particularly now that we're seeing a fairly large. We're seeing more ice giants, or Uranus, Neptune-sized planets in the universe. We're also definitely seeing Jovian planets, so there might be a justification for it. Appreciate it, Tiny Captain. I shaved just because I wanted to see what my upper lip looked like again. I occasionally do that. But I usually quickly grow the stash back. I don't know if I'm going to do that this time. We'll see how long it takes. We'll see how long I like it. All right. Haha. Oh, well, I thought I had fixed these slides. All right. Please forgive the slides. They got transitioned over from one format to another, so they might look a little weird. Giant planets, or the Jovian planets, are known as, or are obviously Jupiter, Saturn, Uranus, and Neptune, in that order from closest to furthest. Jupiter and Saturn are, like I said, called the gas giants. And in this picture, you have the planets to scale in size. Obviously not in distance, but they are scaled in... No, I think I'm going to back off that statement entirely. No, that is correct. That is correct. So this is the scale. These are the planets to scale in linear size. Now, Jupiter, as it says on the slide, Jupiter and Saturn are primarily composed of hydrogen and helium. Now, this is why I think the subcategorization of the ice giants might be a little misleading, because really all four planets are mainly composed of hydrogen and helium. It's just that the ice giants have a small or a slightly larger concentration of ice crystals in their upper atmospheres. But all four of them are primarily composed of hydrogen and helium. Hydrogen and helium being the most conspicuous or the most abundant gases in the universe. The universe only started with hydrogen, helium, and a little bit of bit of lithium. Now, I don't know where I saw this, but I believe it was yesterday or the day before, probably somewhere on Discord, maybe in a YouTube comment section. I don't know. But I've frequently heard that Jupiter is considered to be a failed star. I really, really disagree with that assessment. I have a problem with that because of the fact that I look at things, I look at the definition of things from a formation standpoint. Jupiter did not form in the same way that a star does. It doesn't go through the same formation mechanism. And so this idea that if you just dump more mass on it, it will become a star. Yeah, no. Because of the fact that Jupiter may in fact have a rocky core, which the sun never had. So while it is possible that you could Thanos your way into dumping a lot of mass on this thing to the point that you could crush the interior to get to a temperature of 10 to the 15th Kelvin to initiate hydrogen fusion, uh, I think it's really a disservice to think of Jupiter as a failed star. It is simply a gaseous planet. Again, because of formation. That might seem like a semantic argument, but I think it is very important to realize this because of the fact that Jupiter, it speaks to that Jupiter came into existence in a much different way than stars do. And I think that is like I said, I think that is a fairly vital point to be made. As I said, Uranus and Neptune are also composed of hydrogen and helium. You can see their vital statistics. They also like long walks on the beach. All of them, I don't know if that's just a consequence of being gas giants, but like I said, the Uranus and Neptune are markedly smaller. They are an order of magnitude smaller than Jupiter and Saturn. And so again, that kind of goes to the motivation for subcategorizing them. And they, again, have much more water ice, and also methane ices, ammonia ices, that sort of thing. So what we see here, and this is what was confusing me before, the upper picture is the planets to scale in terms of linear size. So just kilometers. The bottom picture is the planets to scale in angular size. So this is what the planets would look like if you were looking through a telescope, and Jupiter was that angular size. Saturn would be that much smaller in comparison through a telescope, and then Uranus and Neptune really just kind of look like points of light. You can kind of see that it's a disk, but not really, which is one of the reasons why I typically don't show Uranus and Neptune through our telescope, because, yeah, they just kind of look like disk-ish stars. They don't twinkle, and they do look blue, but for me, it's really not a lot of bang for your buck. Yes, and Thanos was very much misunderstood. So the discovery of the giant planets. Well, obviously, Jupiter and Saturn were discovered by the first person to look up and notice that these twinkling lights, or these lights, moved with respect to the background stars. Now, that's often attributed to the Greeks, but I'm pretty sure people before the Greeks figured out that those lights were a little different. Uranus and Neptune, not so much. These are fainter than the human eye can see. They are, Uranus is roughly 8th magnitude, and the lowest you can see in the darkest sky is 6th. So it's what we refer to as a binocular object. You can see them through a good pair of binoculars, but you certainly can't see them with your eyes. And Uranus was discovered by accident by William Herschel in 1781. As with many things, during that time, it was very fashionable to try to look for comets and look for asteroids. People really wanted to make their name in that field of study. And so a lot of really interesting objects were found by people that were not comets. Herschel did find a few. I think he found like 3 or 4 comets, but he's most notably known for discovering Uranus. Now, why or how did he know that he discovered a planet, or how do we know that he discovered a planet? Because one, while it did move with respect to the background field of stars, it didn't move in a cometary-like way. It also never grew a tail, and so it was the characteristics of the orbit which indicated to us what that it was in fact a planet as opposed to a comet. What is your favorite rock planet and gas planet? Well, if we're talking about in the solar system, and I know this is technically may not be considered a rock planet, but my favorite is Pluto, simply because it is so surprising and it has bucked all expectations. So that's my favorite. Gas planet, I'd have to go with Jupiter, mainly because I know Saturn's got those pretty rings. And while Jupiter does have rings, they're certainly not as pretty. I just find Jupiter's bands of color, particularly if you look for or Google images taken by the Juno satellite, Juno, Juno. The images from Juno are just amazing. They are just so vibrant. They are so colorful. You get a lot of different cloud structures. The differential winds in the belts is much higher than it is in Saturn. And so the idea that you have 100-kilometer winds going in vastly different directions because of the high rotation rate, yeah, to me is really, really cool. But anyway, so Uranus was discovered by accident. Now, in a triumph of Newtonian gravity, and really a testament to the idea that gravity exists and it controls the motions of planets, Neptune was discovered through prediction. So when we looked at Uranus, obviously when it was first discovered, we didn't exactly know what it was. Herschel might have suspected that it was a new planet, but really the only way that we could have known that it was a new planet at that time was by looking at it over an extended period of time and calculating its orbit. And when we did that, somebody, and I don't remember who it was, noticed that Uranus's orbit was weird in the sense that it wiggled. So as it moved across the sky, there was on top of it a small but observable wiggle to it. And what was proposed by Gall was that in fact there must be something out beyond the orbit of Uranus that was gravitationally pulling on it, that there was gravitational influence on Uranus based on some outer gravitational object, or some outer mass. And so Gall predicted mathematically where that planet would be, or where that mass would be, and then Leverrier and Adams, a French mathematician and an English mathematician, both independently on their own, without talking to each other, they both mathematically predicted where Neptune should be at a particular time based on Newtonian gravity. And then Gall in 1846, he looked in that area and lo and behold, there was Neptune. There was a disk-like object, as I've just shown you, that's similar in appearance to Uranus. And as we mapped it over time, as we observed it over time, we noticed that it was in a very similar orbit as to all the rest of the planets. So if you want an excellent early demonstration of gravity in terms of celestial bodies, look no further than Uranus and Neptune. So how do we measure the giants? Now, and this is the first attempts. Obviously, now that we have satellites to go out and circle them and such, we have much more precise estimates of their characteristics in terms of size and radius, mass, density, that sort of thing. But how do the early astronomers, and when I say early astronomers, I mean early telescopic astronomers, how did they measure the sizes of the giant planets? And the way they did so was through something known as stellar occultation. Now, stellar occultation is a general term meaning any object passing through the line of sight, blocking out the light from a distant star. It's different than transit, although it's the same geometry. But it's the idea of stellar occultation. We still use stellar occultation to this day to determine the sizes of asteroids. And the idea here is, again, you have Jupiter in the sky. You have a background star. You notice that there's a background star, and you can predict that Jupiter is going to pass in front of it. And so, just as Jupiter touches it, we can, just as it touches it, we start the timer, and then we wait for Jupiter to move past, and then stop the time, and that can be used to determine the diameter of it. Now, at least the angular. Yeah, that can be used to determine the diameter. In terms of mass, you can use Kepler's third law, and I mentioned this in a previous lecture when I was talking about the Newtonian revision of Kepler's law, in that what Kepler did with Newton's third law, to remind you, Kepler's third law states the period of any object in the solar system squared is equal to its distance away from the sun cubed, generally speaking, the first order. Newton came around and said, well, actually, it's a little bit more complicated than that in a way. And he generalized it, and he said that any two objects that are orbiting around each other through the influence of gravity, that relationship is going to be p squared equal to 4 pi g, the gravitational constant, times a cubed, the distance away from them, the distance away from the two objects, or the semi-major axis away from the two objects, divided by the total mass of the system, the mass of object A and the mass of object B. In terms of the solar system, the reason why Kepler did not see that is that in reality, what Kepler did was he looked at ratios. He said the ratio of one planet with respect to the Earth squared is equal to the ratio of the semi-major axis of a planet with respect to the Earth cubed. And when you do that, all the constants just fall out of the equation. They just basically cancel out. And so that is an example of an empirical law, something that is determined through observations and characterizing that motion. Newton was a derived law in that he used the first principles of gravity, and then he was able to reproduce Kepler's law in a more generalized fashion that allows for its use to determine the masses of really a lot of things, stars, galaxies, what have you. In terms of Jupiter, you can use it. One of the key things that one of the key assumptions that you can do, particularly in this age when the precision of instruments was pretty poor, was that you can basically ignore that second mass, because in this case, the second mass are the Jovian, the Galilean moons, Io, Europa, Callisto, and Ganymede. Ganymede and Callisto, sorry, going from inner to outer. You can observe these, again, with binoculars, really, but you can observe these with a telescope, and you can look at how long it takes to go around. That gives you the period, and you can estimate how far away the moon is from Jupiter as it goes around. You have its period. You have the semi-major axis. 4 pi g is a constant which you can calculate, and that sum of the masses, that mass of Jupiter plus the mass of, say, Io, In this case, again, because of the limited precision, you can very easily justify that the mass of Io, which is orders of magnitude lower than the mass of Jupiter, just goes away. You can ignore it. It's negligible. And when you do that, you can get a mass of Jupiter that is 314 times the mass of the Earth. I've done this in, I've granted simulations, but I've done this in the lab with students hundreds of times. And it is a very, very powerful tool. And you can follow that up. And one of the reasons for why it is such a powerful tool, as it were, or one of the reasons why we have confidence that this method works, is that if you take the mass as derived from Io's observations, take the mass as derived from Europa's observations, and then Ganymedes and then Callisto's, they pretty much match. They match within the error bars of the calculation. So that illustrates the versatility of Newton's law, Newton's Kepler's laws. Now, when it comes to the giant planets, in a way, this is kind of the problem that we have with Venus, in that we cannot see to the true surface. If you define the surface of a planet as rocky, as where it gets to a rocky or icy surface, like a solid surface, then we can't see them. All we can see are the upper atmospheres of these giant planets, of these gaseous planets. Because of the sheer amount of atmosphere, very much like Venus, it's opaque to visual light going down and actually, or coming off the surface and passing through the clouds and allowing us to see it. And now this way, same thing with gas giants. One of the interesting characteristics of gas giants is their densities. Now, long ago, I talked about looking at planetary comparative planetology, which is where you get rough trends, or you look for rough trends in the solar system based on the physical characteristics. So for the terrestrial planets, again, to first order, as I like to say, the density is around 5.5. Mars is a little bit of an oddball. Its density is around 3.5 or 3.3, somewhere in that range. But the other three planets, they're all pretty much 5.5, or the density of iron and nickel, thereabouts. The Jovian planets have a density very, very close to 1. And while these planets are far more massive than the terrestrial planets, the reason why their density is so low is because they are so much more radiusive. And yes, I am going to make that a word. It is much, much larger in radius. It is more radiusive than the other planets. And so when you look at the density, which is mass per unit volume, the volume is so much more, so much larger with respect to the Earth than the mass of Jupiter is with respect to the Earth. So the density is lower. And as a consequence, one of the things that astronomers like to talk about is the fact that if you put Saturn in a cosmic pool, Saturn would float. Its density is less than that of water. If you look at, I believe it's grams per cubic centimeter, then the density of Saturn is less than 1. The other characteristics are that the planets are all oblate. Now, you may have heard that the Earth is not a perfect sphere, that the Earth is an oblate spheroid. And yes, that is true, but not nearly to the extent of the other planets. What do I mean by oblateness? What I mean is, if you looked at the diameter of the planet along its equator, and you looked at the diameter along the poles, what you would notice is that those two diameters are not equal. The diameter of the equatorial diameter is going to be larger than the polar diameter. The reason for this is angular momentum. You spin something up, it's going to balloon out at the along the plane of rotation, and it's going to shorten, or it's going to basically seem to shrink at the along the axis of rotation. Very much like how galaxies flatten out into disks, or or rather, when we talked about the solar system formation, we talked about the molecular cloud collapsing. Roughly spherical molecular cloud is collapsing, and as it does so, it turns into a disk. Same physics are at apply here. So you have these gas giants which are rotating on the matter of hours as opposed to days, and the fact that they are primarily made of gas, which is a lot more malleable than rock. You have a significant amount of oblateness. Now, in terms of obliquities, obliquity is just a fancy word for axial tilt. Jupiter, there is a large range. Jupiter, for example, has an axial tilt that is 3 degrees, meaning that it's pretty much straight up and down. Jupiter, if you were on Jupiter, you would not experience seasons. You would not experience drastic seasons. There is really no difference between a Jupiter summer in the northern hemisphere or Jupiter winter in the northern hemisphere. There is marginal changes based on the non-zero axial tilt and the fact that it is in an elliptical orbit. But in comparison to the Earth, it's basically nothing. Now, on the other hand, Uranus, as I like to say, is not revolving around the revolving around the sun. It's rolling around the sun. Its obliquity is 98 degrees, meaning that it has extreme seasons. If you remember from last lecture, I talked about the changing axial tilt of Mars. And as the Martian axial tilt got to 60 degrees, then you have a vast change in the summer and winter in either hemisphere. And with Uranus, the same idea is, and incidentally, Uranus is 98%, which means that its northern pole is actually tilted south. Although really what that means is that its rotation is slightly retrograde in comparison to the other planets. North and south, when you talk about the solar system, is very much subjective to our just kind of northern bias. Apologize for all those folks in the southern hemisphere for that. We also have significant, for all of the planets, another way that they are different than terrestrial planets is that there are cloud patterns. There are, in some cases, very, very distinct cloud patterns like there is in Jupiter. And then and then when you go out to the outer planets or go out to Uranus and Neptune, the cloud layers are not nearly as distinguishable. And I'll explain why in a few moments. What we can see is with these cloud patterns, which for Jupiter, and I always get this mixed up, the dark regions are called belts and the white regions are called zones, although I may have that flipped. Now, with Jupiter, Jupiter is rotating very, very quickly. It is rotating twice as fast as the Earth is. A day on Jupiter is, roughly speaking, 11 hours, as opposed to 24. What that does is that because of the Coriolis effect, it causes the atmosphere to develop layers, or what we call Hadley cells. So if you look at the Earth's atmosphere, again, as I like to say, to first order, you have certain directionality to the winds, overall directionality. You have the easterlies, which go from west to east, I believe in the mid-latitudes, and then at the equator and poles, they go in the opposite directions. Again, I might have that flipped, but the key thing is that for the Earth's atmosphere, there are 3 zones in each hemisphere. 2 of them go from either east to west or west to east, and the other one goes in the opposite direction. But because of the rotation speed is so slow in comparison to Jupiter, you really don't have this sort of obvious banding pattern in our atmosphere. The only obvious effect that we really see are hurricanes. They are basically the storms. Those are indicative of, like I said, the Coriolis effect and this idea of different kind of cells in the atmosphere. So when you look at Jupiter, the most obvious thing is, or most well-known thing about Jupiter, if you're just talking about the planet, is of course the Great Red Spot, which is a little bit weird. Now, in the bottom inset, you see the Great Red Spot, but first I want to take your attention to the white spot. The white spot, if you look again, if you Google search Jupiter, you're going to see many of those white spots and only one giant or great red spot. Those white spots are hurricanes. They are Jovian storm systems. Again, they are driven by the shearing factor between winds, a belt that is going 500 or 700 kilometers per hour that way, and then winds that are going 600 kilometers per hour that way. That shearing, that when those two wind systems go against each other, it causes shearing or swirling. And so Jupiter is constantly covered in hurricanes like that, and particularly in those white ones. The Great Red Spot is a little bit weird in that there's only one, and it is persistent. Those white storms that we see, those typically only last for weeks to months, and then they dissipate, go away, and then another one develops somewhere else. The Great Red Spot, we have observations for the Great Red Spot that go back 300 years, thereabouts. Now, while there have been some observations, more recent observations that say the Great Red Spot is shrinking, I've also seen observations that have said that are counter to that. So it might be shrinking or it might not. But the fact of the matter is that the Great Red Spot is a tremendous storm that has a longevity unlike any of the other storms on Jupiter. Oh, also in sense of scale, if you put the Earth on that image of the Great Red Spot, it would swallow the Earth. This storm is larger than the entire planet of Earth. The colors that you see, that is due to the mix of complex chemistry, or a mix of different chemical elements in the atmosphere, a mixture of ammonia, other hydrocarbons, methane to a certain extent, hydrogen sulfide. Jupiter is a chemist's wet dream. There is a lot of chemistry going on in the Jovian atmosphere, and so all of those individual chemical species will give rise to to individual colors. Again, the idea of, and this is again another one where, as I said, these small storms are pretty much white, whereas a Great Red Spot isn't. So it leads us to believe that whatever is driving this, and so storms must be powered, as much like anything in life. In order for something to move, you have to put energy into it. And so whatever is powering the Great Red Spot is probably coming from a much deeper source than the other storms. And so what this means is, as I'll show in a moment, the density or the composition of the atmospheres are differentiated, very much like the Earth's core or the interior of the Earth. And so you have different leading or different layers that have a larger constituent of, so in this layer you may have more methane, in this layer you may have more ammonia, so forth and so on. And so this storm, for whatever reason, we believe is getting its power, it's being generated from a deeper part of the atmosphere, and it's dredging up all that material from that lower region to the surface, as opposed to those smaller, whiter storms. No, I believe I believe that given the time, Clive is probably asleep, although he's been known to show up at different very times. And I am not going to even talk about Roger from Mud Fossil University, because that's just weird. Anyway. Saturn also has these banding patterns as well as Jupiter. They're not nearly as extreme, and the reason why they're not as pretty or not as obvious is because of smog. There is a higher layer or a larger layer of hydrocarbons in the atmosphere of the upper atmosphere of Saturn, which is basically causing a haze, and that causes the atmosphere to become more opaque to seeing the layers beneath it. So it's not completely opaque, so you can see in this image the different brown patterns. Those again correspond to different, essentially, Hadley cells, and those will and that light does penetrate through this haze, but not as effectively as with Jupiter. Now, there's an interesting thing about Saturn that I don't have it on here. There's an interesting thing about Saturn that is not present on any of the other Jovian worlds. For one thing, Saturn has a jet stream near near the southern pole. It has a wavy. You can see it here. I believe it is a black and white in the optical range. This sort of wavy pattern. So instead of a belt or a zone which is linear across the surface, you actually have this kind of wavy jet stream, and this is due to more localized high and low pressure systems in that band or zone. The other thing that is really weird, and I encourage everyone to Google this because for whatever reason I haven't included it in my slides, this jet stream is hexagonal. It actually is a hexagon, so it doesn't go around, the base or the southern pole in a circle. It goes around in a hexagonal pattern, and I don't have a very good explanation for that. I don't believe anyone really has a great explanation for it, but from my understanding, it has to do with the dynamics of a rotating body, of a jet stream going through a rotation of a rotating body at that pole. So now when we talk about Uranus and Neptune, again, with Uranus, you really don't see any banding pattern at all. That is not to say that it is not present. It is just under a very, very thick amount of haze. These planets are not rotating nearly as much as Jupiter and Saturn. Their rotation rates are on the order of 17, 18 hours as opposed to 11, 12. And they're not nearly as radiusive. They're not nearly as large in diameter. And so, again, the brightnesses are smaller and the bands are not nearly as well defined. The Hadley cells are much smaller in number. But you can see with Neptune, there is a little bit of banding. Howdy, Judy. There is a little bit of banding you can see with Neptune because, again, that means that the hazy outer layer or hazy upper atmosphere is not nearly as hazy as it is with Uranus. Now, in the 70s, Uranus and Neptune are not nearly as well studied as Jupiter and Saturn. In recent times, we've had the Juno satellite and the Cassini-Huygens satellite or mission that went out to Jupiter and Saturn respectively. We don't have corresponding missions to Uranus and Neptune yet. There is one going to, I believe, both, called JUICE. This is kind of a new mission to me, so I haven't really looked into it. I know there is a probe to Uranus coming soon or soonish. And the last I heard about that is that NASA was put it up for public. Basically, they want the public to name it. And if it doesn't get named Proby McButtface, I've lost all faith in humanity. So because of that, we are really left with these close-up images that we have are really back from the 70s, back from the Voyager 2 mission, which was launched 76, 77. And in those images, you can see with Neptune specifically, you can see a great dark spot, or what was called the Great Dark Spot. Again, it's a storm system, but we have since made observations through Hubble that do not indicate that the Great Dark Spot is still there. That storm is markedly less. We don't know what the lifespan of that storm was because, again, observations with any detail on Neptune As you might imagine, it is the farthest technical planet out in the solar system. Those observations with any detail are few and far between. So we don't have a really good estimate of how long the Great Dark Spot existed, but it certainly didn't. Obviously, it doesn't exist now, so its lifespan is shorter than the Great Red Spot. All right. So when we look at the atmosphere of these, as I said before, you have a great deal of differentiation in terms of chemical composition. So you have, if we just simply look at the temperature profile, you can, roughly speaking, break the Jovian atmosphere into two layers. You have the troposphere, and then you have the stratosphere, as defined by that classic temperature inversion. Oh, we have a Clive. Speak of the devil, as it were. No, we in fact have not been talking about aliens yet, because again, NDA really can't do it. So as you go from the inner portions of these Jovian worlds, in this case Jupiter and Saturn, really in all of them, they cool off as you go up. So the interiors of Jupiter and Saturn are very, very hot. And then, as with, say, like the sun, as you get further and further out, it cools off as you talk about a larger and larger volume. And then you get to that temperature inversion going into the stratosphere due to UV heating. But I really want to concentrate on looking at, you have, this is more applicable to Saturn, but it is present in Jupiter. You have this haze of hydrocarbons, and then you go down to ammonia ice. Then it wasn't hydrogen. I think I said hydrogen sulfide or something of that nature. What I really meant was aluminum hydrosulfide, ice, water ice, and then water ammonia droplets, and so forth and so on. And then I've also heard that there is water ice lower down. I didn't realize this. I haven't really looked into this. I probably shouldn't even mention it, but apparently ice has different phases. So ice is not just ice. Apparently it can go through various different types of crystalline construction, all the way down to like phase 10 or something of that nature. So ice does go lower down. It also has different phases, as it were, as you go down. These different elements, another reason why these elements exist in these layers is because they are temperature dependent. Ammonia really exists in a stable form at temperatures of 133 Kelvin or less. Ammonium sulfide is 193 Kelvin or less. Sorry to ask a completely unrelated question. Is the dwarf planet Pluto rocky or a gas type planet? Pluto is not a gas type planet. Pluto is a rocky body, but I say that with some hesitation because it probably, again, I don't think it's very well studied, or actually, rather, I don't think I very well studied the more recent results coming out of the New Horizon mission. But there's a lot more ice on Pluto than there is, say, with the terrestrial planets. So it certainly isn't a terrestrial planet in the sense that it is primarily composed of rocky material. There is a great deal of ice on the surface of Pluto. How far down that goes, that is where I'm ignorant. I don't know where that is. I really do need to look into the more recent New Horizons results. So, rocky, icy, not gaseous. And so, vertically challenged planet, yes. And I know you really can't see this very well, but these are the atmospheric profiles of Uranus and Neptune. Again, you have this temperature inversion, very similar to that of the other planets. With Uranus, or Neptune, excuse me, it is more extreme. The rate at which the temperature drops as a function of altitude is steeper. And the atmospheres are not nearly as complicated or not nearly as differentiated as they are for the other gas giants. No problem, Chris. Now, as I said, with the winds and storms, You have equatorial winds that are generated because of the strong Coriolis effect on these storm systems. You can see from the upper, this white line that is superimposed on these planets, that is the direction and amplitude of these winds. And so I'm going to try to make that larger. And so you can see with Jupiter, you have winds at the equatorial region, which can go from the equator south, slightly south. You have winds that are going from, I think that is meters per second. So 100. I'm sorry, I need to look that up. Actually, let me look that up real quick. So I don't tell you. Okay. That's what it is. It's not meters, it's miles. For some reason, they're imperialist. So these are these winds go from, say, 400 miles per hour to all the way to going from left to right, all the way to about 200 miles per hour, very much underneath it. And for Saturn, you have they can get up to 2,000 kilometers per hour. Again, because Saturn is a little bit less, is slowly rotating, the number of Hadley cells or zones and belts are smaller than they are with Jupiter. Uranus and Neptune, again, because of the slower rotation, they're not equally well defined. The other issue with this is, as I said, Uranus and Neptune, and there might be more updated data on this, but Uranus and Neptune are, again, not well as studied, so the wind profiles are not as precisely well known. So I suspect there is a little bit of wiggle. So you can see with Uranus or with Saturn and Jupiter, there's some wiggle superimposed on a larger fluctuation. Here, I would imagine there is a little bit of wiggle that we just haven't been able to observe. Case in point, Neptune. The reason why we don't have a complete profile is because Neptune moves so slowly that we haven't seen the backside of it yet. Again, the only way that we've actually seen the backside of Neptune is when we sent Voyager out there. We haven't seen the backside of Neptune since. We have not seen the opposite hemisphere because, again, it's as it goes around. Is that true? Yes, because of the axial tilt of Neptune. I know I don't want to use. All right, hold on. Up to 432 kilometers per hour, as defined by Wikipedia. You know what? I'm doing a lot of hedging on this lecture. I might actually come back and do an errata video on this, where I clean up some of these values that I've been talking about, and just talk about the wind speeds. But the take-home point that I want you all to realize, and really what I want you to take away from this, is because of the fact that these planets are, as I've said, rapidly rotating, the Coriolis effect will cause these atmospheres, these tremendously large atmospheres, to essentially differentiate in rotation. And so you have these very, very high wind speeds, and you have these very, very high, not only very high wind speeds, but the winds go in opposite directions at very high velocities, or very high velocities in different directions. So, how do you work? And Tiny Captain, if I haven't said hello to you. Like I said, differentiation. Now, in terms of the models of the interior, what we suspect is that you have at the very, very core, you have some size of some rocky metallic body at the very, very core. Basically, that is the kernel of the planet. As I've described before, in terms of planetary formation, Uh, the start of all of the planets came from electrically charged dust particles, minutely sized dust particles that clumped together due to electrostatics. And then once they became more electrically neutral, gravity took over, started clumping them in together. And then once they got to a certain size, the gravity was such that it started bringing in the hydrogen and helium gas, which was the main constituent of these protoplanetary disks. And so these planets quickly, or in a sort of runaway effect, they rapidly grew their planetesimals, and then their atmospheres, and then even faster and faster grew up. And so uh, these atmospheres are primarily composed of hydrogen and helium. As I said, as I just showed you, there are hydrocarbons and methane and ammonia also in the upper atmospheres. Thing that I really want to point out here is that um, both Saturn and Jupiter have a layer of what we call metallic hydrogen. Now, this has to occur at very high pressures and very high temperatures. That actually should be Kelvin, not kilometers. So tens of thousands of Kelvin. And hydrogen can exist in a liquid phase and be conductive to electricity. Hence why it's called metallic hydrogen. It's not actually, I guess, technically like well, depends on what you mean by metal, but it can conduct electricity really well. And it's also in a liquid phase. What I find to be fascinating about this is that, at least for Saturn, Saturn generates a little bit more energy than it receives from the sun. And the reason why it does so is because you have liquid hydrogen raining through the atmosphere. And as it does so, it creates friction with the surrounding medium, and it generates heat in that way. Basically, it's converting gravitational energy, or gravitational potential energy, into kinetic energy and heat. Jupiter definitely produces more energy than it receives. Again, potentially through metallic hydrogen rain, but primarily it's attributed to the fact that Jupiter is so massive that it isn't quite in hydrostatic equilibrium yet. The internal thermal pressure hasn't equalized Jupiter. It is, to this day, still shrinking. Not an overly large amount, but it is observably shrinking. And as it does so, again, it is converting gravitational potential energy into kinetic energy, which then gets radiated out as heat or infrared radiation. Again, as you might expect with Uranus and Neptune, there is no metallic hydrogen phase, because the interior temperatures and phases, or interior temperatures and pressures, are smaller. Because it is less massive, there is there's less gravitational pressure being applied to these worlds. In addition, that also means that there is less temperature, the temperatures are lower. Hence why in the upper atmospheres there is a considerably larger amount of water in liquid phase, and ices, ammonia and methane ices. We do believe there is also some speculation. Oh, hello, cat. There is some speculation that there may in fact be oceans, or regions inside of Uranus and Neptune, that are primarily composed of liquid water that is salty, that there are ammonia salts, or basically there are salty material inside those oceans. Now, again, with these pictures, I've mentioned, I've commented on these before. These are overly simplistic illustrations of what these interiors look like. These interiors are far more complex. There are not these even, smooth lines of transition between one phase to another. To give you an idea of what I'm talking about, oh, I don't have this up here. I guess that's going to be in the next lecture. But to preview the next lecture, which I will talk about the magnetospheres of the magnetic fields of these planets. The magnetic fields of Jupiter and Saturn are what we refer to as poloidal. They look like bar magnets. They are very, very strong, and they look similar in shape to that of the Earth. Uranus and Neptune, not even close. For Earth, Jupiter and Saturn, and Mercury also, you have the rotation axis. You have the axis on which everything moves around or rotates around. The magnetic axis, which is defined by the northern and southern poles or polarity, is also aligned or pretty well aligned with that rotation axis. So Jupiter, Saturn, and the Earth, well behaved. It makes sense with the dynamo effect, or what we believe is creating these magnetic fields. For Jupiter and Saturn, again, you have these metallic region or metallic hydrogen regions. You can have currents which flow through that metallic hydrogen region, which in turn generates a poloidal magnetic field. Uranus and Neptune, not so much. Not only do the magnetic axes nowhere even close to align to the rotational axes, but the center of the magnet, if you think of this as a bar magnet, the center of that magnet isn't in the center of the planet as it is for Earth, Jupiter, and Saturn. It's off to the side. So these magnetic fields are bonkers. And again, one of the reasons, or one of the justifications for this hypothesis of deep oceans that with these salts is because of how this can explain how these magnetic fields can be so weird. So basically off center, off kilter. Now, why these oceans are so asymmetric, why they seem to be on one side of the core rather than or one side of the planet than the other, I don't believe that is very well understood. So, all right. And with that, I will leave you all, bid you all clear skies and peace. But I will say that I need to double check. Actually, I will check now on Discord. Okay. They haven't responded yet, so I'm going to take that to mean that I win. So in about an hour, I am going to go live again, and I am going to go live with our telescope. So I am going to get on. I'm going to actually walk to my office, and I'm going to open up the telescope, and I am going to do some observing tonight. And I welcome you all to take part in that if you're awake and whatever. I did this a while ago when a couple of weeks ago when I looked at globular clusters. Tonight, I hope to be able to take some images of galaxies, specifically my favorite galaxy, because this was also happened to be the first galaxy that I took digital photographs of, and that is the Whirlpool Galaxy, which is two galaxies that are interacting with each other. It's a beautiful, beautiful galaxy. If you follow Hubble images, I'm positive you've seen this thing before. So I'm going to do my best to image that. If I have time, I will go to a different galaxy, hopefully an elliptical galaxy, so I can compare and contrast for folks what the difference in what fancy term for it is morphology. Compare and contrast the different appearances of spiral galaxies in comparison to elliptical galaxies. So I hope that you'll join me for that. I am going to go live around 9. Again, I have to get over there. I have to set things up, but that is my plan, to go live in 1 hour from now. So, all right. As always, I hope you found this educational and entertaining. If you like this sort of thing, please like, share, and subscribe, and all that goodness. All right. And if you haven't already, like I said, I have posted a video on Venus. It's a short video showing what we can do here at the observatory with our planetary cam. Highly recommend you go check that out. It's like 5 minutes. And I ramble on about the Venusian phases. All right. I'm out of here. Peace out.